Now, just before I get into the lecturing of material, what I want to do first is just quickly to go back to the TypeScript lab and just run through some of the exercises on it. I'm not going to spend a whole lot of time on this. I should really have done this much closer to when I gave you the lab, but it didn't work out that way for me. So just to give you a quick refresh, if you remember, let's say if we open up this file here, we had a friend type and we had a colleague type. We had some other types as well, but we also had a buddy type, who could be a friend or a colleague. And then just run down through some of the uh, exercises. That's really all I want to cover. So, for example, there was a, let's see, there was a all older function that you had to write. The function took an array of friends and it returned a string for each friend stating what did it state? It stated, I think, what their new age was, their name and their updated age, so to speak, which happened to be the exact same as what was returned by a function that I gave you called older. So this is the return string. So really all you had to do in the case of all older was just to map over to map over the array of friends and call older for each one of them. Yeah, that meant now that over here we have an array of strings with the right structure, and I just returned that array. What some people did was they essentially kind of took this code here and they copied it and put it into the callback that you passed the map. You didn't really need to do that, but the other exercise in this file was a find friends method. Where is that? This one here, find friends. And what you passed it was an array of friends and the criteria by which you identified the friends that you were interested in or finding. And really the trick there was also what this find friends had to return was just the names of those friends. So it was a string array. And simply then all you had to do was call filter on the array of friends. That gave you a subset of friends. And then call map on that subset of friends and just return map over them and just extract their name. So filter and map really was the key to that. Now, of course, what many of you did was to chain on the map onto the filter, which is a better way of writing it rather than having this as two separate lines. And also, yeah, the other function, sorry, in this file was an add interest. And that simply took two parameters. It took a friend parameter and a string parameter, where the string was the new interest that we wanted to add to that friends array of interests. If we go back to friend, interest here was optional. It's an array of strings, but it is optional. So you could have a friend that currently doesn't have any interests, And that was the kind of catch, if you like, in the implementation of add interest, because what I'm doing here is I'm first of all checking to see, there's f is a friend, f dot interest. Is that evaluate to true or false? If it's true, that means we already have an array of interest for this friend. Then return that if you like and apply it to that. Otherwise, create an empty array and assign the empty array to friend.interest, and then just push the value, the new interest, onto that array. Now, if you were doing this in JavaScript, you probably, unless you were very diligent, you probably would leave out this line. And it's not until you ran this it's not until you invoked this function with a friend that didn't have any interest array, it's only then that would throw an exception, because we would try to invoke the push method essentially on the undefined value, because f.interest would evaluate to undefined, and you cannot, the undefined value doesn't have a push method associated with it. But you wouldn't discover that flaw in your implementation until you actually ran your code and you passed it a friend object that did not have an interest property in it. And that may never occur, uh, or it would occur eventually. And that's why with JavaScript, errors occur only when it gets, you've got a particular piece of data which causes the error to occur. In this case, the error would be, the data would be a friend object that doesn't have an interest property. But the beauty with TypeScript is that it will tell you about that weakness in your implementation at compile time. And that's what we're seeing here. It's essentially telling us, if we open up the problems tab, it's saying this is possibly undefined, and therefore you can't invoke push on undefined. And that, in a nutshell, really is the beauty of TypeScript. It spots these edge cases in your code at compile time. Moving on to this file here. Here you had to implement a method called getBuddyListFriends. So the idea of this method is you pass it in an array of buddies, where a buddy could be a friend or a colleague, and you wanted to just extract the friends within that buddy list and return that array of friends. Yeah. So, and I think I did also say that you should try to use the array reduce method in your implementation. And so that's what we're doing here. We're calling reduce on a buddy list, if you remember, had as a property a list of buddies. So list.members here that evaluates to an array of buddies. And I'm just essentially iterating over that. But I want to pick out, in that list, I just want to pick out the friend objects. I'm not interested in the colleague objects. Yeah. And so that's what that line of code is doing, because if we went back and looked at the friend structure and the colleague structure, the friend structure, let's just do that. The friend structure has a phone property, whereas the colleague structure does not have a phone property. So that was the way of distinguishing between a friend and a colleague within our buddy list. So that was the essential, that line there that I've highlighted was the key part, but most people actually got that. The last thing I look at is in this file here, and what you had to do was, let me see, where is it? Not that one, sorry, this one here. I gave you the outline for this function, which is past an array of friends and an array of colleagues, and it had to find the intersection between those two arrays. Okay, so you could have a person who is both a friend and a colleague, and the way you identify that was if the name of the friend is the same as the name of the colleague. That's what we decided. Um, and what it should return then. So that's easy enough to work out that. But what I wanted the function to return was an object which had, sorry, I wanted to return an array where the entries in the array had some properties from the friend structure and some properties from the colleague structure. But I said you should define that new type using utility types. Yeah, and that's where a lot of people fell down. What a lot of people did was that, in my case, if we just take this type here, right? I said in the lab, I told you exactly what properties were in this type that I've highlighted, but those properties were being taken from the friend type and the colleague type. And so you kind of had to reflect that in your implementation of this new type. And so, for example, where have I got it? Oh yeah, so here's the type in my case, this new type. And I'm using the pick utility type. I'm using it twice actually. You could have used the omit utility type as well. I didn't really care which utility type you used, but straight away, from in terms of somebody else reading this code, they can see, look, there's some sort of relationship between the friend and the colleague type and this type here. Yeah, and that's kind of what utility types are useful for, showing you the connection between one type and another type. Okay, in terms of the implementation of that particular method, uh, what I did was, where do I have it? How did I do it? I kind of invoked the reduce over my array of friends, and then in each case, I checked to see if that friend is in the colleague array that was passed in. And if they were, then I knew they were both a friend and a colleague. And then I just create a new instance. Here I'm creating a new instance uh, of my kind of combined type, if you like, my intersection type. Although I'm not stating that this object here is an instance of this friend and colleague type, which it deducts that anyway, or it infers that, sorry. But it might have been clear just to say, to add on the as clause here to say that this interpret this as an instance of friend and colleague. Okay, that's that. Just pause for any questions in case there are any questions. It's a very quick run through it, admittedly. No, okay. What I found was most people had Most people got everything right except this very last part. What a lot of people did was they just simply defined a new type and gave it, explicitly gave it this structure without actually using the utility types to define this new structure. Okay, back to the website. So I want to start a new topic, which I could have given it any number of titles really. I'm just going to call it messaging. Messaging is quite a um, let's call it an old label, but it's very relevant to newer types of applications that are deployed on the cloud. Now, there is a lab that will accompany this, but I decided just to leave the lab out for this week because you're hopefully concentrating on the first assignment. So next week I'll reveal the lab that's accompanying these slides. And the lab will actually span over maybe 2 or 3 weeks. So I want to start looking through this set of slides. So we're turning our attention to a set of services which kind of come under the general heading of messaging services or integration services. And we're going to be using the CDK again to create resources related to these services. So we're never going to get away from using the CDK framework. So the title on this slide is Components of a Serverless Message-Driven Application. So we're still going to bring all that serverless stuff with us, although the whole area of using messaging within an application predates serverless. And that's a kind of comment that I will probably make a number of times as I work my way through this set of slides. But we do use messaging a lot in the serverless kind of architecture as well. There is another kind of more succinct name for applications that are heavily utilizing messaging within their architecture, and that is event-driven architectures or an application with an event-driven architecture. Event-driven architecture, I guess, would be a new kind of label, and it kind of implies that it's serverless and it's message orientated. Before serverless, as I said, messaging was still a feature of application architecture, but we would have just used the label a message-driven architecture. And in the image then, we're kind of down here at the communications side of an application's makeup. And in particular, we're looking at these two services, the SQS service and the SNS service. So they are within the kind of the area of facilitating communications between the compute components in your in an application. Now, if it's a purely serverless application, then the compute components are more than likely Lambdas. But if it's not a serverless application, the compute components could be an actual EC2 instance that is running some subset of an application. It could even be a container running on the Amazon cloud. There are Amazon services specifically for hosting containers. We haven't looked at it and we won't get to look at it, but they are there. So the compute components within an application could be a Lambda, could be a container, could be an EC2 instance, and or a combination of those. And whichever it is, or whatever kind of combination that you have, if you want to allow one component, whether that component is a Lambda or a container or an EC2 instance, the generic name is, let's call it a component. If you want one component to be able to communicate with another component, and these components are going to be communicating over a network, then those components could communicate directly or synchronously, or instead they could use these intermediaries to facilitate communication. And we'll see all, how this pans out as we work our way through these slides. So why do we need messaging? And I'm going to talk about it, assuming now that our compute components are just Lambdas, but it doesn't have to be just Lambdas. So if you've got this kind of feature in an application, you've got a number of Lambdas and they are communicating with one another. So, let's say a client, whatever a client is, it could be a mobile app, it could be a desktop app, it could be a web app. A client sends a request to a Lambda. Now, there might be an API gateway in here. We don't really care about that detail. Either way, the client wants to trigger the execution of this Lambda here. And the detail of what this Lambda does is not important. It does some processing of the request. Maybe it writes some data to a database. But as part of the processing carried out by this Lambda, it delegates some more processing to this Lambda. So it communicates synchronously with this Lambda. This Lambda does whatever it's supposed to do, carries out whatever processing, may involve actually also maybe reading, maybe this Lambda writes some data to the database, maybe this Lambda reads that data and does some processing of it, and maybe does some updates to the data or whatever, we don't really care. And even maybe the processing done by this Lambda, as part of it, it delegates some of that processing to a third Lambda. These Lambdas now are not instances, micro VMs of the same code. They're completely different Lambda functions, but they kind of collectively complete some overall processing that's required of the request that came in here. And the key thing, though, is that the communication links here are synchronous. Okay, they're over a network, but they're still synchronous. Now, what we mean by that is, and if you look at the kind of numbering that I've given these lines, the client, first of all, sends a request to this Lambda. It does some processing, and as part of that processing, it communicates with this Lambda. So we're on number 2. As part of the processing done by this Lambda, it communicates with this one, number 3. Now, meanwhile, this Lambda here is waiting for a reply back from this Lambda here. It's a synchronous communication link. And if this is waiting, then that means our client is also waiting for the response back from this Lambda. But that response doesn't happen until this starts executing, and this starts executing. It's only when this Lambda completes its execution and it responds back, sends a response back to this Lambda, which it may need to do some processing of. Eventually, this Lambda will respond back to this Lambda, which may cause it to do some further processing. And finally, this Lambda then responds back to the client. So there is synchronous communication between these compute components, and that means that our client has to wait until all of this processing is completed before it gets a response back. it may be the case when you study it in more detail that really let's say the processing done by these two lambdas is not of a nature that the client actually has to wait for that processing to complete. And there are cases when that arises. Okay, and so if that's the case, that these two lambdas here, um, essentially they can kind of do their processing offline. Uh, and by offline, I'm just using that term kind of broadly here. By offline, I simply mean that the client does not have to wait really for that processing to complete. Now, how could we actually achieve that is what we want to try and do. And the answer will be use messaging, which we'll talk about in the next slide. The same thing can kind of happen if you've got a Lambda that does a lot of processing, you know. But maybe, and it's not until all of that processing is completed that our client gets its response back. Um, you know, maybe there is certain parts of the processing that's done inside in this Lambda, which really can be done asynchronously. When I use the term offline there, maybe asynchronously might have been a better term to use. So how can we sort of break up this Lambda such that the processing that can be done asynchronously can be removed from it? And that means now that this Lambda can respond quicker back to the client. And so there is less latency from the client's point of view, latency being the time between the request was issued and the response that came back. And it's that issue of latency that we're trying to tackle here. But if we go back to this example, right, how can we sort of make the link between these two asynchronous rather than synchronous, which means we can send the response back to our client more speedily, lower latency. So here I'm just talking about, the problems on the previous slide. So whenever you've got synchronous communication between compute components, which happen to be lambdas in our case, this can be problematic if there are certain spikes in demand and or gaps in availability. And I'm just giving an example here. Supposing we've got a lambda, like if we actually think of this case here and apply it to here, maybe the client, what it does is it uploads a video, and the purpose of this lambda is simply to store that video into an S3 bucket. And then this lambda here, what it needs to do is it needs to process that video, maybe check that the video is suitable for viewing. And maybe this lambda converts the video into different formats and stores those other different formats in some other S3 bucket. Now, does the client over here, does it really need to wait until these two lambdas have completed their processing? Really, all the client is interested in is, did you save my video to the bucket? And let the other lambdas do their processing kind of asynchronously. If there is suddenly a high demand, like a high volume of uploads happening to our videos, and we're still staying with this kind of synchronous approach, then okay, this lambda here might be able to handle the high volume of uploads because all it's really doing is storing the videos into an S3 bucket. But this lambda or this lambda may not be able to deal with the high volume of requests that it's receiving from this one. So, either or both of these lambdas may actually time out or throw an exception because they can't handle the volume of requests that are coming at it. Even if we do, even if we spin up multiple instances of these lambdas, it still may not be capable of dealing with the high volume. And so that now means that our client over here is probably going to eventually receive a throttling response back from this lambda because these guys can't actually deal with the volume. And we're still assuming now that there is a synchronous communication going on between uh, these various components. And if it is synchronous, then, as I've already explained, this one is waiting for this one is waiting for this one, and so on and so forth. So a certain spike in demand for this kind of an architecture is problematic. The other thing I'm talking about here is if there's problems with availability. By availability, we mean, let's supposing for whatever reason, this lambda is not contactable. Maybe it's on an AZ zone that is down temporarily, which means that when this lambda tries to communicate with it, it's not getting any response, and therefore it can't respond back to here. And so our client is now waiting essentially, or maybe getting, this may eventually throw an exception to the effect that I can't contact this lambda. That exception is going to be returned back to here, and it's going to return back to here. And so now our client is just getting a standard kind of inaccessible type of exception error. So when you've got this kind of synchronous communication going on between compute components, um, there are lots of problems with it. There is the latency problem, there is the spike in demand problem, and there's the availability problem. Okay, that's what I'm trying to get across there. I'm saying it's better to decouple your components, decouple your compute components by using messaging, which we'll see in a second. Now, in the case of AWS, there are a number of messaging services available to us: SQS, SNS. There's also something called data streaming, which we'll briefly look at the end. And when you start introducing these, so maybe if I go on to the next slide before I talk about this. So the idea here now is this component, if we stick with the video, this component receives the video and stores it at an S3 bucket. And it will send a message, it will post a message into this resource here. This is a message queuing resource. It'll post a message essentially to the effect that a new video has been uploaded to the S3 bucket, and the video's name, file name is whatever. Now, this lambda here, note the direction of the arrow, right? What this lambda does is it periodically checks, are there any messages in this queue? And if there are, then it reads those messages and it processes them. And in the case of our video example, that will mean each message will contain the name of a video file. And so this lambda will read that file, read the files, and do its whatever processing it's doing of them, scanning them for viewability. Maybe when it's finished, when it has finished scanning a video and it's happy that it's viewable, it will then post a message into this queue, which is being polled by this lambda. And this lambda, sticking with my example, this lambda now knows that it can get the particular video that has been scanned by this one and is suitable, and it carries out maybe some conversion of that video into different formats. And so we've decoupled these three components from one another. Now the flow is client contacts this lambda, kind of uploads a video. The Lambda stores the video in the S3 bucket. It writes a message to the queue, and then it responds back. Note the numbering now. So it can respond back saying, I've got your video and we've saved it. It can do that before either of these Lambdas have done any processing of that video. So the messages in this example, the messages would contain details about the videos in our S3 bucket. And so we have decoupled our compute components. And it seems, using that video example, that seems like a sensible thing to do in this case. In some cases, it may not be sensible to do the decoupling, and you have to go back to your original architecture. You go back to your original architecture when it's absolutely essential that all of the processing done here and here and here needs to be completed before you can go back to the client and say, we're done. Here's your response. And so from a latency point of view, our clients now get a response back much quicker. Let's go back to here. So I'm saying there is reduced latency, increased availability. What I mean by that is, let's supposing this Lambda is running on an AZ zone that's currently inaccessible. That doesn't matter, because the messages this Lambda can continue to write messages to this queue as it's working its way through the different videos that it needs to scan. But the messages will remain here until this Lambda becomes back online again. Its availability zone is accessible again, and it will start reading the messages and do its processing. So temporary unavailability of either of these Lambdas can be dealt with. The messaging service kind of will hold on to the messages until eventually our Lambdas actually kind of read them. Now there is a limit as to how long a message will remain in a queue before the service that's managing these queues. There is a service that's kind of managing these. Okay, if it's an SQS queue, it's the if it's a queue, it's the SQS service, and that's just a server that's just managing the addition and deletion of messages, and it's also dealing with requests from the Lambda to find messages and return it back to the Lambda. But yeah, so the SQS service will hold on to messages in case a particular consumer, as it's called, doesn't request messages over a period of time, i.e. it's unavailable for whatever reason. Availability, increased. Well, it's not so much increased availability, but if something is unavailable for a short period, that's not a problem. Reduced complexity, yeah, I mean, arguably, for somebody that's looking at this application from the beginning, you weren't involved in the development of it, and you're trying to gain an understanding of how this application works, then when you see these kind of synchronous connections, you have to kind of get the entire picture, develop an understanding of the entire sub-architecture in your mind. Whereas in the decoupled approach, you can essentially treat these as separate, independent, and so you just need to understand them in isolation of one another. So reduced complexity, decreased dependency. Well, dependency and coupling are interlinked. So there is really now there isn't really any dependency relationship between these three lambdas. They're independent of one another. Okay, they're connected via these messaging queues, but relative to one another, they're completely independent. So what we want to look at really is from a pure technical point of view, how do we create these messaging resources? How do we hook them up to lambdas, and also get maybe a little bit of an understanding as to the inner workings of these uh, messaging resources. So there are, from AWS's perspective anyway, there are two main messaging services, SQS, which stands for Simple Queue Service, and SNS, which stands for Simple Notification Service. So we'll look at SQS first. And the very first thing we need to note is that SQS was the very first service that AWS offered uh, to the community. It was before we had EC2 instances. Obviously, it was before we had Lambdas. It was before we had any of the other AWS services that you're familiar with. Before S3 buckets, before EC2 instances, as I said, certainly before DynamoDB, or before any database service. Okay, so and why did they choose? Why did they think that something like a messaging service would be useful to the community? Well, if I go back, well, we've got it here actually. Their vision at that stage, so we're way back in 2009 or 2006, sorry, was that um, software houses had applications that ran on their own services. Remember now, we didn't have EC2. We may not even have had virtualization as a concept. So organizations had applications running on their own services, on their own hardware, what we refer to as on-premise hardware. But organizations want to be able to communicate with applications of another organization. Your kind of typical scenario is you've got a purchaser and a seller, okay? And when a transaction happens between a purchaser and a seller, then rather than that happening at a paper level, we'd like the purchaser's applications to be able to communicate with the seller's applications, invoicing, shipping, etc., etc. Now, we could, if the two organizations were close, I guess, from a business point of view, we could have a synchronous connection. In other words, this organization here could have a REST API, which could be invoked from this application here. So that would be a synchronous link, but we know what the problems with that are. And so what AWS decided was, let's make these a messaging service, let's make it available so that this application would now, rather than having a synchronous connection, this application can write messages to this queue. This application can read messages from that queue. So we decouple them. So that was where SQS, or that's why, or that was sort of the main kind of use case for SQS back in 2006 to facilitate communication between different organizations' own on-premise applications, inter-application communication, I guess you'd call it. Today, what we use SQS, it's still probably being used in this scenario, but what we're interested in this module and where SQS is used a lot today is to facilitate that kind of link between lambdas, that asynchronous link between lambdas. So, you may have client API gateway, Lambda writes messages to queues. Maybe this Lambda also updates a database, puts messages into a queue, and this Lambda here, processes those messages. Uh, so, um, so the SQS service is a fully managed service. So there is actually an SQS server that needs to manage the queues. Fully managed was a byword that we've been using a lot for serverless, but of course, fully managed back then, serverless wasn't a phrase back in 2006, but it kind of it was a forerunner to the idea of serverless. As we'll see in a while, SQS is also distributed inherently. We don't actually control it. Uh, you might remember when we were talking about DynamoDB and the way DynamoDB was, we had these kind of partitioning going on, and also we had replication going on of a database. Again, that was completely managed by the DynamoDB service. We had no control over it, but there was a lot of distribution behind the scenes. Similarly, there's distribution of our SQS, or there's distribution being performed by SQS, as we'll see. So it's a fully managed distributed queuing service used to decouple applications/components. So it was, again, it was originally for decoupling applications, entire applications, but more generically, it's for decoupling any kind of compute components. Your compute components role. Okay, so there are essentially two roles that a compute component may have within this setup. There's a producer component and a consumer component. And producers are components that write messages to the queue. Consumers are components that read messages off of the queue. Pretty straightforward. Some attributes of SQS. It's fully scalable. So it doesn't matter what volume of messages are being written to the queue. SQS will guarantee that it will hold on to all of those messages until a consumer has processed those messages. So it's completely unlimited. Doesn't so that's kind of deals with our video example there, where we had certainly a spike in demand. That doesn't cause any problems from SQS's perspective. SQS does actually persist messages, but there is a limit to it. So the default is that it will persist messages for 4 days. And that's the default. You can set it to up to a maximum of 14 days. And the reason we have persistence at all, well, there are kind of two reasons. One, maybe the consumer is very busy. So although it is reading messages off the queue, it's not reading them at a rate that allows it to, consume the messages as quickly as they're being written. Also, if our consumer components are unavailable for whatever reason, they're on an AZ zone that's not contactable, then that's not a problem. The messages will remain in the queue until it becomes online again, as I was talking about earlier. So there is a certain amount of persistence of messages within our SQS queues, although it's not persistence doesn't persist for as long as a database might persist data, which is essentially kind of forever. Low latency, all I'm getting at there is that when the producer is writing messages to the queue, then SQS has kind of limits, has guarantees, sorry, about how quickly it will receive those messages and write them into a queue. Obviously, that's kind of important, if we go back to here. So we're talking about SQS now as being the messaging service here. If I can write SQS. So here's our producer. And even if it's writing messages at a very high rate, then SQS gives us certain guarantees about being able to handle high volumes of write requests. And similarly, if this, which is our consumer, if our consumer is requesting messages at a very high rate, the SQS service has certain guarantees about being able to deal with that high volume of demand for read operations. So we don't have so there's kind of certain guarantees that the AWS people give to us about the latency from the producers or consumers' perspective. Um, so that's the latency issue. Now there is a limit of 200 and what 256K. That's the upper limit for the size of a message. There's ways of getting around that, but that's just an arbitrary limit that they have imposed on any users of this SQS service. Um, some caveats. Number one, um, uh, if you read the documentation about SQS, it says like that there are uh, there may be cases very infrequent, but it's not. It's just warning us about it really that a message may be duplicated within the queue, which means it may be consumed twice by a consumer. It's very rare, but it's just sort of, as I said, it's informing us that it is possible that a consumer may receive the same message twice. Now, if that's the case, then we've got to ensure that our consumers are idempotent. Idempotent means that they can deal with that kind of case. And you have to kind of program that into your consumer component. I'm not going to, there are techniques for achieving that. We don't really need to get into it, but we just need to be aware of the fact that it is possible that we will never see it happening because we're going to be dealing with very small volumes of messages being written and read by our lambdas. But in the case where there is a high volume of messages being written to an SQS queue, then it is possible, the AWS people say, because they've obviously done extensive testing of their SQS service. And what they have noticed is that consumers, in very rare cases, may actually receive the same message twice. And um, secondly, AWS tell us that you don't have any guarantee about the ordering of the messages from a consumer's perspective. Okay. We will actually see that, all right, in our case. Well, we may see it. Certainly when I've played around with it, I have certainly seen it. So there's no guarantee that the consumer receives the messages in the same order in which they were written into the queue. If you do want the ordering to be preserved, then you need to configure your queue to achieve that. And that's referred to as a forgotten what the actual term is now. But if you do configure a queue to uh, to ensure that messages are consumed in the right order, then your latency values are actually increasing. So it takes SQS a little bit longer to honor that requirement, if you like. Uh, an ordered queue, I think, sorry, that was the term for it. So if you want an ordered queue, you can configure it for sure, but you do lose in terms of latency um, as a result. So anyway, there are only caveats. We're not really too concerned about either of them. So from an operations point of view, it's pretty straightforward. So we know already that there are two our compute components are either producers or consumers. What does the producer do? It publishes or writes messages to a queue using the SQS SDK. So as before, every AWS service provides an SDK so that we can communicate with that service, and that's the case for SQS as well. So if you want, let's say, a Lambda to write messages to a queue, you simply use the SQS SDK within that Lambda, and we'll see that happening in a while. The SQS will persist the message, as I was saying, although there's a limit to that. And it'll persist the message in the queue until either A consumer deletes the message. So it's the consumer's responsibility to delete messages from the queue. Okay. Secondly, if no consumer, well, a consumer obviously will read the message first, and when they've finished processing the message, they are responsible for telling SQS to now delete that message from the queue. I guess that's what I'm getting at here, right? The consumer reads the message from the queue, processes that message, and then it is responsible for telling SQS to delete that message. If it doesn't do that latter part, then the message will remain in the queue, and the same consumer or another consumer may get that same message again. And presumably we don't want that. That's different now from the duplicate messages case that I was talking about earlier on. So it's the consumer is responsible for telling SQS, you can now delete this message from the queue. The other case is when the producer writes or publishes a message onto a queue, that message has what's called a time to live, or TTL, and you can control that from a configuration point of view. If no consumer reads a message before the TTL has expired, then the SQS service itself will delete that message from the queue. And the default TTL is 4 days, which is kind of like what we were mentioning earlier on. But you can set it to be more than that or less than that. The maximum, as we saw in an earlier slide, is 14 days though. But you can configure that at the queue level, not at the message level, now at the queue level. So messages will persist in a queue until either A consumer explicitly requests the deletion of it, or B, the message's TTL has expired. What do we mean by a message? Like, a message could be anything, typically a JSON structure, but it can be anything in terms of its meaning, right? So typical simple scenario might be a publisher writes an order message to a queue, where the or might be, whatever the various properties of an order are, order ID, customer ID, the list of products, etc., in JSON form. That might be a message. The consumer then is the other compute component, and the consumer, this is how it behaves. So it polls the SQS for messages. Now, if I go back, to a couple of slides, and I'm just going to clean up this. I've kind of mentioned it in passing, but like the direction of the arrows. So this Lambda is writing the message to a queue. When a producer writes a message to a queue, this Lambda is not triggered straight away about that fact. And that's why I've got the arrow going in this direction. This Lambda is responsible for periodically checking to see, are there any messages in the queue? And that's what we call polling. So the Lambda polls the SQS service, essentially asking it, have you got any messages? So there may be none, there may be some, there may be an awful lot. Yeah. And the frequency with which it polls is again a configuration setting. And you would clearly kind of tune that to be based on how frequently you think messages are going to be written to the queue. If the messages are written, a couple of messages every hour, then presumably this Lambda doesn't need to poll the SQS service more frequently than, let's say, once an hour or something like that. But it polls it anyway. The consumer polls. So this Lambda is not triggered immediately after this Lambda has written the message to the queue. Hence, they're kind of asynchronous. So go back to here. So it polls SQS for messages. It receives a batch of messages as a response. The batching here is important. So from a consumer's point of view, excuse me, you must always treat the response that you get back from SQS as a batch of messages, even if the batch only contains one entry. And we'll see that in a while. A batch is always going to have less than or equal to 10 messages. So I think SQS controls that. So even if it has 100 messages in the queue, it will only return 10 of them. Yeah. And our consumer processes these messages. And as I've already said, finally, the consumer tells SQS, you can now delete the batch that you gave me. Okay. So this is kind of a visual of how all of this works. There's a synchronous kind of communication between our producer, which happens to be a Lambda, and the SQS service. There's a polling communication between the consumer and the SQS service. And when we look at these two Lambdas relative to one another, it's an asynchronous link, if you like. I mean, there is a link between them by virtue of the fact that they're both kind of talking to the intermediary here, the SQS queue, but they're not synchronized with one another. Hence, it's an asynchronous and somewhat indirect communication link between our producer and our consumer. So that's the kind of flow of communication, or the communication style there, as I've put it in the heading. Security point of view, always a big factor for AWS. We have in-flight encryption for free. AWS does that for us. What I mean by that is, because this link here is over a network and this link here is over a network, AWS will encrypt the communication here and the communication here. That's in-flight communication. It will also encrypt the messages that are being stored in the queue. That's called at-rest encryption. And as I said, all of that is done kind of for free by SQS, by the SQS servers for you. From an access control point of view, surprise, surprise, IAM is involved. So the producer has to have the necessary IAM privileges to write to a queue. The consumer has to have the necessary IAM privileges to read messages from the queue. And we also have what are called SQS access policies, which, a bit like with DynamoDB, if you want to allow another AWS account to be able to access a queue that has been created in your account, then you need to define that in an SQS access policy. We don't really need to, we won't see that. Also, if you want some other service to be able to write to a queue, it's not just Lambdas that can write messages to a queue. Other services can as well. but those other services need to have the privileges to do that. And so those privileges would be defined in an SQS access policy. I think we'll see an example of where the S3 service, when we upload a file to an S3 bucket, then the S3 service will write a message to a queue. So the S3 service needs to have the necessary privilege to do that. And we'll see that a little bit later on. Okay, simple demo. The demo is comprised of a queue, an SQS queue, a Lambda, which is reading messages from the queue, and our publisher is just going to be, we're just going to use the AWS CLI to write messages to the queue. So that's technically the publisher. Now, there's a slight lie in what I've been telling you so far, and it's the following, right? So here's my Lambda function, my consumer, and here's the Lambda service. Now, it's not the Lambda function that directly communicates with the SQS service. The Lambda service does that for it. So it's the Lambda service that polls the SQS service for messages from the queue. And that means that the SQS service will respond back with a batch of messages from this queue. The response goes back to the Lambda service, and the Lambda service then simply invokes our Lambda function, and it passes the messages that it received, it passes those within the event object that this Lambda receives as part of its invocation. So again, I'll say that, right? It's the Lambda service that's periodically polling the SQS service, asking it, do you have any messages in a particular queue? The batch of messages will be returned to the Lambda service, and the Lambda service, it invokes your function. And we know that the invocation includes two arguments, the event object and the context object. We never really looked at the context object, but the event object in this case will contain within it the batch of messages and some other properties as well. And that's what I'm explaining down here. Oh yeah, the final piece of the jigsaw is, so now our Lambda function has been invoked with the messages that are contained within the event object. So it extracts the messages from the event object and it does its processing. And it completes its processing. Then the Lambda service, it actually asks or tells the SQS queue, you can now delete that batch of messages. So it's the Lambda service that is responsible. It takes care of the kind of cleanup operation. So you don't have to have any code in your Lambda function. In fact, your Lambda function here, it's not communicating directly with SQS at all. The Lambda service is doing it on its behalf. If my consumer over here was an application running inside an EC2 instance, then my application code, it would have to take care of all of that. It would have to take care of the polling. It would have to take care of getting SQS to delete the messages. So I would have to write within my application code over here, I would have to write all of the code that deals with communicating with SQS. Whereas when it's a simple Lambda function, the Lambda service does all of that low-level interaction for me, which is kind of neat. Okay, we'll just look at the code and then we'll run it. So here's the CDK stack for the simple application that I had on the previous slide. We've got a Lambda function, and its configuration. There's no evidence from looking at the configuration of this Lambda function that it's actually talking to SQS at all. Oh yeah, this line here, sorry. This is where I'm creating my SQS queue. So I'm creating a queue. Implicitly, it's an SQS queue. So this is creating a queue, but behind the scenes, it's the SQS service that takes care of creating an empty queue for me, which is just, a piece of memory, I guess, that it manages. It manages that memory. This is my Lambda function, as I've said. And this is the part where you indicate that this Lambda is actually a consumer for this queue. So this is kind of how you hook them up. So you create an instance of an SQS event source. That's the term in the CDK world. As in, SQS is the event source for my Lambda. Remember, we said Lambda is an event-driven compute resource. So what's the event in this case? Well, the event is kind of being provided by the SQS service. So in terms of creating an instance of this, you've got to tell it, well, sorry, the kind of the first line of code is creating an SQS event source independent of any consumer. Okay. The second line is where we connect up this event source with our Lambda function, as in we add an event source to this Lambda function. Okay, so it's a two-step process really to connect them up. What am I saying down here? Recall Lambda functions are triggered by an event. That's okay. Here the event source. Well, I've kind of already said that really. All that's left then is the internals of this Lambda function. And that's what I'm showing you here. So it's a Lambda. And as always, it takes two parameters, although I'm only interested in one of them here, the event parameter. I am indicating that this particular Lambda, its type, if you like, is an SQS handler. And that determines the structure of the event object. The other type we had was we had a Lambda that was being triggered by API gateway. That handler had a different type associated with it because the internals of the event object would be different for an API gateway triggered Lambda as opposed to an SQS triggered Lambda. As usual, I'm console logging the event just for debugging purposes. Now, this line here, the for loop, you can see here I'm referencing a property within the event called records. Now, straight away, that's telling me that this event object, although it's evident from here, right? This event object is somehow linked to a messaging service. Records here, you could think of records as your batch. I'm trying to access the batch of messages within the event. And I've said on numerous occasions that it's always going to be a batch. Even if there's only one message in the batch, you still have to treat it as a batch. And a batch is essentially an array, which is why I'm looping over it. So record here is going to, as we loop through this, record is always going to be pointing at one of the messages in the batch, and I'm just console logging the message. This is how we are going to trigger this is how we're going to write a message to our queue, just using the AWS CLI. So I've already deployed, let's go over to VS Code. And is this the one? Yeah. So very quickly, my CDK stack, which I've already shown you, create a queue. Sorry, no. Create a queue. Here's my Lambda. Connect them up together. And I'm outputting the URL. The queue has a URL associated with it. That's how you, well, that's how we're going to be able to send messages using the CLI. So I'm outputting the URL. And you can see here, this is the URL of the queue when I deployed it earlier. And so if I flip over to my console, so I don't have any log groups at the moment. Just check that again. So I have the URL of my queue, and to send a message to that queue using the CLI, let's just go back through these. Okay, so it's just AWS SQS send message. What is the URL of the queue? And then what is the message body? So I'm just sending it a simple string as the message in this case. So when I hit return here, the CLI will communicate with the SQS service and ask it to put hello world message into the queue. Then at some stage, the Lambda service is going to poll that queue. It will receive a batch of messages. There'll only be one message in that batch, the message that I've just posted down here at the bottom. And the Lambda service then will trigger my Lambda function. So I should have, because in my Lambda function, I have sorry, here's the Lambda function. I've got a console log. We should see that in CloudWatch. And I've commented out all this stuff. We're not interested in it right now. So let's just hit return down here at the bottom. So I've written a message to the queue, and if I refresh here, okay, so this is the log group for my Lambda. And the console log of the actual event that the Lambda service passed to it. Here's the event object that this Lambda received, which, if you go back and when we console logged the events associated with Lambdas that were triggered by API Gateway, those events had a very different structure to these events, and that makes sense, right? One of the properties, as we can see in the event, is a property called records. And as I was explaining when I was looking through the slides, the records property, you can see here, it's an array. And so the records property, it's going to be the array of messages in the batch that were received by the Lambda service from the SQS service when it polled it. Now, because there was only one message, there's only going to be one, because I only published one message, there's only going to be one in this array. And so my message starts here and finishes here. And the only property we're interested in is the body property. There's some other useful stuff in there as well, but we're not interested in it right now. And you can see in the body, it indeed has the message that I sent to the queue. So that proves that my consumer Lambda was triggered, um, and it got the message. Now, if I do, uh, if I go back to the stack file, so we said that these two lines here are how you connect up your Lambda function to the queue and make the queue kind of the source of the events that will eventually trigger my Lambda. Even though my Lambda, when we look at my Lambda code, it's not communicating directly with SQS at all. But if we look at the configuration of the Lambda from the console, so if we go into the Lambda service, and in particular, so here's my entry for my Lambda. In particular, I'm interested in the permissions that this Lambda has, the kind of IAM permissions. So we go into configuration and permissions. And we talked about the execution role. The execution role of a Lambda controls what that Lambda, what other services that Lambda can use. Now, so let's look at the role. And the role has two policies associated with it. The first policy is the standard one that every Lambda gets. That's the policy that allows it to write to CloudWatch logs. What's this second policy about? Well, if we look at it, and this second policy was dynamically generated by my CDK. And it has in it stuff relating to, if we look at this one here, right? It's saying, well, this Lambda can receive messages from SQS. The other ones, it can also, this Lambda has permission to delete messages from an SQS queue. Now, the reason the Lambda is assigned those privileges is because the Lambda service won't be able to communicate with SQS on behalf of this Lambda function unless this Lambda function has those two permissions. So it's a little bit kind of confusing to an extent. Like I've said that when we look at our Lambda code, it's not communicating with SQS directly at all. So that would suggest, well, it doesn't need any IAM policy that gives it permission to interact with the SQS service. But somehow the CDK generated this policy, which indicates that the Lambda does need permissions to interact with SQS. And the reason the CDK does that, and it's not really the CDK, it's really the way Lambda as a consumer of an SQS is designed. The Lambda function needs to have the permissions before the Lambda service will carry out those actions on its behalf. Okay, I'll say that again. The Lambda function needs the necessary permissions to interact with SQS, i.e. receive messages and delete messages. The Lambda function needs those permissions to allow the Lambda service to carry out those actions on its behalf. If we got rid of those, then it just wouldn't work. The Lambda service wouldn't be able to communicate with SQS. So it's kind of the security side. But that's what's happening behind the scenes. And really, this policy was generated and attached to the Lambda's execution role as a result of as a result of uh, essentially this line of code here. Okay, I'll pause for a question in case there is any question. All right, let's move on. Yeah, I've shown you that in the demo, so it's just a screenshot. Now, we just sent a string there as our message, but, typically a message is some sort of JSON structure. And what I'm saying here is that when the SQS service receives a JSON structure as the message, it serializes that JSON structure. And that's what eventually your Lambda will receive. It will receive a serialized form of the JSON. And clearly it cannot process that. It needs to parse it. So it's just something that you need to remember. Let's do a quick demo of that. So I've got a simple JSON file here. Okay. Email address and name, address, and email. So let's supposing I want to send that JSON as a message into my queue. And how you do that using the CLI is, if you can see here down at the bottom, you can reference a file, a JSON file, as being the message body. Don't know if that's showing up clearly on your screens, but here I'm just referring to, and the protocol needs to be as I'm showing it, as I'm typing it here. So if I send that, and I now go back to CloudWatch and look at the message that my Lambda received, just need to go back to the right region now because it always switches back to North Virginia. Where are we? Europe. So we're in CloudWatch, into our groups, our group, and okay, it's created a new log stream. Let's check the timing. So it looks like this one here. That's a new micro VM. And here's the console log. Again, there was only one message in the batch. And if we look at the body of the message, you can see that it has serialized my JSON structure. Okay, now if I go back to the Lambda itself, actually, so at the moment, all I'm doing in the Lambda is just console logging the event. But if I want to process each individual message, then if I now just re-enable this code here, and as I said, it's just a simple for loop iterating over the batch of messages. And I know that this is the structure. So I've just, for convenience, I've defined a type for myself to match the JSON structure. And I just want a console log. the person's name in the JSON structure, and their address. All right. Okay, so I need to redeploy, CDK deploy. When I'm redeploying here, it's going to hold on to the same queue. So it does not generate a different URL for your queue because I haven't made a change. I haven't made any changes to that queue. And even if I had changed the configuration, it would still be the same URL. That's just a by the way, you don't have to go copying the URL every time. So, okay, it's done that. And if I now resend my JSON structure, and go back to CloudWatch and do some refreshing. So a manual refresh. Okay, and this looks like the stream. So my Lambda now has two console logs. This is the console log of the entire event. This is the console log of just the name and address. And if I expand that, look, it did extract my name and it extracted the address as well. So that's fine. And I mean, within the loop, you can see that I had to parse the JSON. I had to parse the body of the message. That's all that's going on there. And I've mentioned the fact that SQS serializes any JSON structures. Okay, moving on. That's okay. And that's, oh yeah. Now, I've actually taken this screenshot directly out of the SQS, AWS's SQS documentation. And I mentioned the fact at the beginning there that SQS is inherently distributed. And this is kind of what I'm trying to get at in this slide here. So when you create an SQS queue, and we saw how to do that at the CDK level, and you start putting messages into that queue, behind the scenes, what SQS does is it actually distributes the queue across a number of nodes, or a node is just, some hardware. Well, it probably might be a virtual machine, but ultimately on hardware that's distributed across the network. And so that's kind of what we're showing here, right? And it looks like in this queue, there's messages, and the messages are simply labeled A, B, C, D. So publishers would be on the right in this case. When publishers write a message to this queue, what the SQS service does is it writes that message to a subset of the nodes that make up this queue. So for example, if you take message A, it's written it onto this node and this node and this node and this node, but it hasn't written it on the other nodes. So each of these is a node now, which is a separate machine, if you like, hardware machine, that is persisting a part of our queue. How it distributes these nodes and which node it selects to write a message to, that's completely under the control of AWS. We have no control over that. So as producers write messages to this queue. And from the producer's perspective, it just sees one queue. The entire thing is the queue. But when it writes a message to the queue, what SQS does is it decides arbitrarily which particular node it will persist that message to, and it won't persist it to all of it. Hence, there is distribution. And the reason it does that again is got to do with availability. So if this particular node here is on as an AZ zone that is unavailable temporarily, then at least we know that message A is going to be on the other nodes. And whenever a consumer requests to consume some batch of messages from the queue, then it may well get that message A from these nodes. Now, on the consumer side, now we have three consumers here, but let's assume there is only one consumer. On the consumer side, when it asks SQS for a batch of messages, what SQS does is it arbitrarily selects a subset of these nodes, and it does that based on some algorithm. We have no control over it. So based on the kind of coloring here, let's supposing it selected this node and this node and this node. It reads a batch of messages from those subset of nodes that it has selected. Now you can see that A appears here and A appears here. Now what SQS will do is it will know that, look, it's not going to give back two copies of A back to the consumer. It will eliminate any duplicates that it finds, having selected a subset of nodes. It will delete the duplicates, and then it will eventually return back individual copies of the messages that it found on the nodes that it had selected. And if there were more than 10 messages, if there were a couple of hundred messages on each of these, then it will still only pick 10 of them. I won't say it's the first 10 because there's no notion of the first or last. It'll just select 10 messages. And if there happens to be duplicates within any one of those messages, it will ignore the duplicates. When I'm talking about duplicates here now, this has got nothing to do with the point that I made earlier on, which was that in very rare cases, duplicates, your consumer may receive duplicate copies of the same message. It will never receive the duplicates within one batch, but across a set of batches, it may receive duplicates. And the reason that happens is because, the next time this consumer polls SQS, then maybe this node is selected and some of the other nodes, and A is actually here again. And so A would be returned back to the consumer a second time. That's when duplicates do occur. But you can be guaranteed that you will not receive duplicates of a message within a batch. So the overall point is this idea that there is the actual AQ is actually distributed across a number of nodes being managed by the SQS service. When a producer writes a message to the queue, SQS will automatically make multiple copies of that message. It won't make a copy onto every node. It will only make a copy onto a subset of nodes, and that subset is completely arbitrarily chosen. And on the consuming side, when the consumer polls SQS, SQS selects a subset of the nodes, and it takes messages from that subset of nodes. Something I didn't mention at all, and really goes back to the very early days of SQS. You can see here I have three consumers, right? Now, technically, you can have more than one consumer for a queue, but the way queues work is that only one consumer will be allowed to process a message. And by that I mean, if this consumer receives message A and it processes message A, and well, let's say, look, it receives this batch, this consumer here, consumer 2, receives this batch of messages and it processes them all successfully. And it tells SQS you can now delete this batch. We're not saying this now as a Lambda. Let's assume it's an EC2 instance, an application running inside an EC2 instance. It tells SQS to delete that batch, and SQS will carry out that. Then let's supposing this consumer now polls SQS for a batch of messages. Well, clearly it will not receive any of these messages because they've already been deleted. If, having received this batch of messages, the consumer crashes, which means it never asks SQS to delete them, and then this consumer comes along and polls SQS, then it may actually receive some of these messages because they haven't been deleted. And if this consumer successfully processes the batch and gets SQS to delete them, then we can be guaranteed that these two consumers will never get any of the messages that were successfully processed by the other consumer. So if you have multiple consumers, you can be guaranteed that two consumers will not successfully process the same message, and the successfully is important. If you want the situation where you do want all of your consumers to process all of the messages, then you don't use the SQS service. You use the SNS service, which we'll talk about in a later lecture. We could equally have two lambdas here to demonstrate all of this, but I'm not going to go through that, but you could have multiple lambdas polling the same SQS queue. And, it would be difficult to illustrate to you all the different scenarios that can arise. But what you can be guaranteed is that, let's assume these are lambdas now. If one lambda successfully processes a batch of messages, you can be guaranteed that the other lambdas will never receive any of those messages that were successfully processed by the first lambda. Okay, watching my clock. I think I'm not going to get into this here now because I would need more time than is available to me to explain the scaling, but the scaling that happens is quite interesting actually. And again, it's not obvious that this scaling is going on behind the scenes. So I'm going to stop at this slide here and pick it up next week with you. Do have a few minutes left, just in case anybody has any questions in relation to the assignment. I'm assuming people are working on the assignment because you only have this coming week, the coming week actually, this week and next week to work your way through the assignment. So are there any questions in relation to the assignment? I haven't received any questions on Slack so far. I'll take that as a good sign. No. Okay. I will leave it at that for today. So there's no lab for this week. But as I said at the outset, hopefully you're working on the assignment. I will still turn up at the lab classes tomorrow morning, and I may talk to you then. Okay, that's it for today. Thanks. Bye-bye.